This is a brief tutorial on force and doing force problems. It's really designed to give you a basic idea of what a force is and how to do these problems. So we'll start with what a force is. A force is anything that is capable of causing acceleration. I really like this definition. It's from an old colleague of mine who really captured the idea. So forces cause accelerations, and a force is anything that's capable of causing an acceleration. So it could be gravity, it could be a spring, it could be a rod, it could be a cable, anything that's capable of causing an acceleration. So forces are vectors, and we can define the vector quantity mathematically using Newton's second law, F equals ma. And a lot of time we'll write that the net force, which is the vector sum of all the forces acting on an object, is the F net is ma. So the net force is an interesting and important concept. The net force is the vector sum of all of the real forces that act on some object, and forces act on objects. So there are some common forces that we're going to encounter in Physics 1 problems. The first one is weight. And weight is the force associated with gravity and gravitational acceleration g. And the weight always acts downward. And we draw that with this downward arrow. And we can make pictures like this. We draw the forces acting on objects. And in this case, the one force that I've drawn is the weight. And the weight is equal to mg, the mass times the gravitational acceleration. So weight is a very common force that we'll run into. The arrow of weight points downward, and the weight is mg. Another common force is tension. So a tension is the force that's produced by a taut string or a rope or a cable. And these kinds of forces, these tensions, can only pull objects because you can't push on a rope. And here's a little example. It's a tension pulling a block along the surface. So the tension vector is right there. The tension vector points in the direction pulling the direction of the cable. And we usually take the tension to be the same everywhere in a rope or a cable, unless the rope passes over a massive pulley. So if you have a single rope, the tension is taken to be the same everywhere, the magnitude of the force it creates. Now, there are some common problems, and one of them is this so-called Atwood's machine. Here's a mass 1 and a mass 2 that are hanging connected together with a pulley, with a cable over a pulley, via this cable. And notice that the tension in each case is the same in magnitude, and the cable pulls the mass up. So the tensions are pointing in that direction. So the same tension is acting on mass 1 and on mass 2, pulling in both cases. So tensions in cables are very common. Cables always pull, and unless there's a massive or a friction pulley, the tension is the same everywhere in a cable. Another common force is friction. Specifically, we mean sliding friction. And it's actually coming from an electromagnetic force between surfaces. Friction always acts to oppose the motion that is or will occur. So for example here, when a block is sliding down an incline, the frictional force opposes the motion and acts upward. So friction acts parallel to the surface of contact. We can write the frictional force quantitatively as the frictional force is mu n. So mu is the coefficient of friction, and this mu is tabulated. There are huge tables that relate different materials on other materials. Rubber on asphalt, steel on wood, and so on. So huge tables. Also, the mu depend on whether or not the object is sliding. If it's not sliding, if it's still at rest, we use the coefficient of static friction. If the object is already sliding along a surface, then it's the kinetic coefficient. So static and kinetic. Friction is extremely common. We talk about sliding one surface across another, and this normal force we'll come to in just a moment, because friction depends on the normal force. So let's talk about the normal force. So that normal force that we just talked about, that appears in the frictional force, is the force present when one object is in contact with another on a surface. So, for example, you sitting in your chair, there's a normal force, the chair pushing up on you. In this case, we have a block that's sitting on a surface, and there's a normal force pushing upward. It's the surface, the table, pushing up on the block. We call it the normal force because it acts normal to the surface. And in this case, you can see the surface presses upward on the mass. So we find these normal forces anywhere there's physical contact on a surface, and the direction is always perpendicular to the surface. So for our incline again, here we can see that this block is sitting on an incline, and there's a normal force acting upward in that direction perpendicular to the surface. That's the normal force of the incline pressing up on the block. The last force we'll talk about is a little less common and a little more complicated, but it's so important to physics in general that we really ought to talk about it. It's the force due to a spring. And the force due to a spring depends on how the spring is stretched or compressed from its equilibrium point. At equilibrium, the spring exerts no force. When you displace from equilibrium, if you stretch the spring or compress the spring, the force is always directed back toward equilibrium. That is, toward the unstretched case. So for this reason, we call the spring force a restoring force. It wants to restore to equilibrium. And for this simple spring force, the force magnitude and direction is given by minus kx. And the minus is indicating back to equilibrium. So if we start at, let's say, an equilibrium point here, unstretched spring at x equals 0, when we stretch the spring to that point, the force due to the spring, due to the stretched spring, is back toward equilibrium to the left. So the spring force is minus kx, the x is positive, so the force is to the left or negative. So here we see this property in motion, in practice. If we compress the spring, then the spring force points to the right. It's always back toward equilibrium. So here, the x is negative, it's displaced to the left of equilibrium, and the force is now pointing to the right. This k is very interesting. It's the spring constant. It's really a measure of how stiff the spring is. The stiffer the spring, the larger the k. Okay, so let's work on some problems. You really learn how to do physics by doing the problems. It's really about the practice. Okay, so these problems are not hard, and there are a few steps that can guide you and get you going. Okay, first step, which is super important, draw a picture. You don't have to be a great artist. I'm a terrible artist. My sister's a real artist. I can't really draw very many things, but I can draw a simple picture and then draw the forces acting on each mass or element or object in the system. So the key here is to draw the picture and then decide these are the objects, these are the masses or blocks or whatever, and draw all the forces that act on each block. Now, that could be a pretty complicated picture, and real physical objects are extended things, blocks and people and planets. What we often do is draw a simpler picture called a free body diagram. In a free body diagram, you reduce all of the elements, each individual object, to a point. So we get this much simplified picture that just consists of points representing each object or each mass, with forces acting on it. Okay, this next point I said is very important. So this is something that people don't often talk about, and I remember struggling with this material until I really decided or discovered this is what we should do. So it's really important to choose a coordinate system. So usually the picture helps with this, and what I mean is you have to decide consciously what the x direction is, what the y direction is, and what positive means. Now you can make any choice you want, and a lot of the time it's really dictated by the picture. You can make any choice you want, but you have to choose and stick with the choice because that's going to drive how you write the equations and use the picture. So once you've decided where x and y are, the directions, then you can resolve forces into components. You have decided on the directions, so now write the net force, MAX, and then add up all the forces that have components in the x direction, all the x components. Add up all the y components. So now you'll have a set of equations. The net force, MAX, equals the sum of the x components. MAY equals the sum of the y components. And you're really almost done. Now, finally, you're going to use what you know and solve. So what do you mean by use what you know? Well, if the object's at rest, the net force is 0. If it's moving constant speed, the net force is 0. Maybe you know the acceleration. So typically you know something in the problem that sort of guides you to make it possible to solve the problem. And then finally, we never want to leave that out. Does the answer make sense? The beauty of Physics 1 is that you probably already have great intuitions about how things work. And you can use those intuitions. Does the answer that you came up with, the force or the acceleration or the motion, does it actually make sense to you? If it does, great. If it doesn't, you have to find out, well, did I have an incorrect expectation? And if so, why? Did I make a mistake? Or both? Let's do some problems. Okay, so we're going to start with a really simple problem. A 100 kilogram mass slides on a frictionless surface. A rope pulls with a 50 Newton force as shown. So we want to find out what the acceleration is. So here's our picture. So there's a normal force, there's a tension, and there's a weight. So remember I said draw all the forces. So there's a normal force, the surface is pressing upward, there's a weight, mg, and then there's this horizontal force of tension, 50 newtons. Now we draw a free body diagram. Notice how the mass has become just this point. So it's a point with the same forces. That's an example of a very simple free body diagram. And we don't worry about the size of the block. I mean, its physical extent. It's a point. It's a point mass. So now we draw a coordinate system. We decide on the coordinate system. So I say, well, this is the x direction, and this is the y direction, and this is the plus x direction and plus y. So I decided that's the coordinate system. Could I have made a different decision? Of course. But that seems like a reasonable choice. Okay, so I'm going to write the net force in each direction. Well, the net force in the y direction, MAY, is the normal force upward and the weight downward. That's it. The net force in the y direction is N upward and mg downward minus mg. In the x direction, that's really simple. The net force in the x direction is just the tension. There's nothing else. So now I have two equations, one for the net force in the x direction, one for the net force in the y direction. Now, this block is not going to fly off the table. There is no acceleration in the y direction. So I can use that and say MAY is N minus mg. So I set AY equals 0. That means the normal force is the weight. That's a common occurrence, but it is not always true. Now, in the x direction, it's even simpler. Now, I don't know the acceleration in the x direction, but that's what I'm trying to find. So I can just solve for AX. AX is the tension over the mass, or 50 newtons over 100 kilograms. That's half a meter per second squared. Beautiful, simple problem. Look, we drew the picture, we drew the free body diagram, we wrote the forces, we solved. Every problem is going to look like that. Let's do a more interesting problem. So here we have a block that's on a surface again, but there is friction. And there's a tension of 5 newtons pulling on this 5 kilogram block, but the tension is now at an angle, right? It's got a 30-degree angle. And I want to know what the acceleration is. Okay, same thing we did before. Let's draw all the forces. There's a tension. There's a weight. There's a normal force. The table's pressing upward. And in this case, there's a frictional force. Now, the frictional force is going to oppose the motion, and we can see that the motion is going to be to the right, so we draw the frictional force to the left. Now we're going to draw our free body diagram. So we reduce that block mass to a point, right? Tension, weight, normal force, frictional force. Decide on the coordinate system. This is going to be the x direction plus x plus y. Okay, now we're ready to allow this this picture to drive the equation. So the picture drives the equation. In the y direction, what do we have? Well, we have the net force in the y direction. There's the normal force upward that we see in our picture. There's the weight downward, minus mg, and there's a component of the tension upward, t sine 30, t sine of the angle. So we can't forget that component of the tension, and we see it there. The tension has this component upward. Once again, the block is not supposed to fly off the table, so we're going to say that the acceleration in the y direction is 0. Boom. So I can now write out the normal force. The normal force is just 95.5 newtons. Now, why do I care about the normal force? Well, I care about the normal force in this problem because it's going to play a role in the friction. So let's look at the x direction. So the net force in the x direction is a component of the tension to the right, T cos 30. That's the piece of tension along the horizontal. And the frictional force from our picture is to the left. And notice that now I'm going to write out the frictional force as mu n. But I know n now. So I can actually plug everything in. 5 cos 30, that's the tension cos 30. That's the component of tension along the x. And then mu n, mu is my coefficient of friction. 95.5 is the normal force. So I can actually solve for that right-hand side and then solve for the acceleration. The x acceleration is 0.3375 meters per second. So again, a slightly more sophisticated problem. It's got tension and friction. Now there's an interesting thing that can happen. If the frictional coefficient is large enough, we could actually end up in this calculation with an AX that's negative. What the heck would that mean? How could the acceleration be negative to the left? Well, it can't be, actually. The frictional force is not going to cause this to move to the left. If the acceleration becomes negative, that really means that the mass is not going to move at all. So the acceleration has to be 0 or positive in this problem. And if you got a negative acceleration, that just means that the frictional force was large enough to prevent the motion from occurring. That is, friction keeps it from accelerating. So it's a result that you will sometimes see. Let's talk about a mass on an incline. This is actually an interesting problem, and it's one that crops up quite often in different forms. So here we put a mass on an incline, and we ask a slightly different question. How large does the frictional coefficient, mu, need to be to keep the block from sliding down the incline? So we're going to put this block on the incline, and it's supposed to sit there. The frictional force is large enough to keep it from sliding, so it has no motion and no acceleration. So look, we draw our picture. There's weight, there's a normal force perpendicular to the plane of the incline, and the frictional force we're drawing that way because it's opposing the motion. The motion without friction would be down the incline, it would slide. Now we have this wonderful little free body diagram. There's the normal force, the weight, the friction. Now notice that because of the incline, I'm going to pick the x direction here and the y direction there. So I twisted the coordinate system to make one of the coordinates, the x coordinate, parallel to the motion, or the motion that would occur. And that's going to make my problem way easier. It has to be possible to work any problem in any coordinate system. But this coordinate system is going to make your life easier. Okay, why or how? Well, let's talk about the y motion in this case. So the y motion is along this direction right here, right? So the net force in the y direction is the normal force minus a component of the gravitational force, this component right there, right? So the net force in the y direction, which is perpendicular to the plane of the incline, would be n minus mg cos theta. And once again, this block is not going to fly off the incline. It's supposed to sit there. So the net force and the net acceleration are 0, which allows us to write the normal force as mg cos theta. Again, this is a rather common result for inclined plane problems, but you have to be careful. It's not always the case. So armed with that normal force, we can now attack the x direction and try to find the coefficient of friction. So look, the x direction, the net force is mg sine theta. That's this component right here down the incline due to gravity, mg sine theta, minus the frictional force that's opposing it. So I could go ahead and substitute in there, right, for mu n, and then actually put in everything mg sine theta minus mu n, where n was this, this thing I found over here. Now, the key to this problem is there is no acceleration. It sits there at rest, which means that ax is 0. So I can actually make this very simple and then do a little algebra and solve the required coefficient of friction. In this case, it would be static coefficient because it's not moving. It's just the tangent of the angle. So this is actually a really interesting result. The mass drops out. The mass doesn't matter. So no matter what mass you have, it will still sit there as long as the coefficient of friction is large enough. And all masses experience the same 0 acceleration in this problem. Let's do a pulley problem with no friction. So again, this is kind of a common problem. We have a mass that's tied with a rope to a second mass, and here we've labeled them mass 1, mass 2. It's a frictionless pulley, no mass on the pulley. So let's draw the forces. Well, the forces on mass 1 are the normal force, right? It's sitting on a surface. There's this cable or string that provides a tension, and then there's weight. Now, the second mass has a weight pointing downward. It has a tension from the rope, and notice that it's the same tension magnitude, T. Now, the ropes only pull, so the direction of the rope acting on mass 2 is as shown. Now, our free body diagram gets a little more complicated because we need a free body diagram for each of the masses. So here's the first one, the mass 1. There's the normal force, there's the tension, there's the m1g. And then for the second mass, it's m2g and t. That's just reducing the masses to points. Now, here's a really important thing. Really important. When I decide the coordinate system, I'm going to connect together the motion of that thing and the motion of that, because they're tied together. They have to have the same acceleration and the same motion because they're connected. So it's very useful to use the coordinate system to connect them. So I'm going to say this motion, the sort of clockwise motion, is going to be positive. So I'm going to call positive x here, and this is also going to be positive x because I want the x motion of mass 1 to be the same as the mass 2 x motion. So I'm connecting the horizontal motion of m1 to the vertical motion of m2 using the coordinate system. And of course, for mass 1, there's still a plus y. So this is a very important step. It makes your life much easier if you choose this coordinate system to connect the masses. So when you have a mass connected with a rope over a pulley to another mass, you want to connect the motions with the coordinate system. And I did that here by calling that one plus x and that one plus x because the plus x's match. The accelerations will match. Let's talk about mass 1. Look, mass 1 in the x direction in my picture right here, the m1ax, the net force on mass 1 in the x direction, there's only one thing there, t. Right there, t. T. In the y direction, the net force in the y direction for mass 1, m1ay, is the normal force minus the weight. The block does not fly off the table, so the acceleration is 0. So I can now find the normal force acting on mass 1. Now, mass 2, notice I have mass 2 m2ax. Notice that ax is there and ax is there. It's the same ax. It has to be because they're connected together. In this case, we see that for mass 2, there's m2g pointing downward, which we called plus x. The tension acts upward, right? Upward. So it's upward is minus in this case, so minus t. All right, so I have two equations here and here. I have to do some algebra. I substitute in for t, m1ax, and I do some algebra, and I solve for ax. That's the acceleration of m2 downward and m1 to the right. Here's another common problem, the Atwood's machine. It's just two masses connected over a massless, frictionless pulley, and typically we want to find the acceleration. Okay, so here's our picture. Notice that there's a weight, m1g, there's a tension, there's an m2g, a weight, there's the same tension. The ropes pull up. We have to draw this free body diagram for each mass. So here's mass 1. It's got a weight m1g pointing downward, a tension upward. Mass 2 has a weight downward, and there's going to be a tension upward. Okay, and remember I'm going to choose this motion carefully. I'm going to say, well look, this is the plus x motion. That is this sort of clockwise motion. So I'm going to call for mass 1 plus x, mass 2 plus x is downward. So look, the motions are connected. Upward motion of mass 1 corresponds to downward motion of mass 2. That's a beautiful thing. So let's write the forces. Okay, look, the net force acting on mass 1 is T minus mg. Look, T is in the plus x direction, m1g is in the minus x direction as I've defined it right there. Mass 2 m2ax, the net force on mass 2, is m2g. So look, that's right there in the plus x direction as I've defined it, m2g, downward. Tension is upward. That's in the minus direction. Now there's this common thing that happens in these sort of tension problems with pulleys. Notice how the tension here is positive and the tension here is negative. When you see that, it probably means you're on the right track. Usually we see this kind of thing occur. So we can solve one of these equations for the tension. I solved the mass 1 equation. We can then plug in for the tension here in the second equation. And then we can finally do some algebra and solve for the acceleration. Now, one thing that we can kind of guess here is, look, if the masses are equal, mass 2 and mass 1 are equal, if you look at it, it's just going to hang there, right? I mean, it isn't going to accelerate. It's balanced. So look, our equation m2 minus m1 in the numerator means that when m2 and m1 are the same, we get zero acceleration. Notice that when m2 is larger, the acceleration is positive, which means it's going to be in the clockwise direction. When m1 is larger, it's negative. Exactly like we expect. That's beautiful. Okay, our last little problem. This one's more complicated. Okay, you have to think about this one. So I have a mass 1 sitting on top of a mass 2. Mass 2 is connected with a cable over a frictionless light pulley to mass 3. And there's going to be friction between mass 1 and mass 2 and between mass 2 and the table. And there are going to be different coefficients of friction. So between mass 1 and mass 2, we'll call that mu12, and between mass 2 and the table, mu2t. So here and here, those two interfaces. So for mass 1 to stay on top of mass 2, mass 1 has to have the same acceleration as mass 2. It has to be possible for that to happen. So if the acceleration of mass 2 is larger than mass 1, mass 2 is going to slide out from underneath. Okay, it's a complicated diagram now. I'm going to go right to the free body diagram. So for mass 1, there's a normal force upward on mass 1 from that surface. There's a weight, and then there's friction. Notice that friction is pointing to the right. Friction is actually going to drag this mass along. Without friction, the relative motion of mass 1 is it slides off. Mass 2 is more complicated. Okay, there's this tension from the rope. There's a normal force from the table upward. There's a normal force from the mass on top downward, the same normal force N1. There's a weight, and there's two frictional forces, the friction from the top surface and the friction from the bottom surface. And both of those frictions tend to keep the mass from sliding. Okay, if you get the pictures right here, you are really a long way to making the problem work. The last mass looks familiar, right? There's a tension and there's a weight m3g. So I got to connect the motions again. So I'm going to say, well, look, plus x direction is to the right, plus x direction is to the right for the mass 1 and mass 2, and plus x direction is downward for mass 3. So it's this, right, this clockwise motion again. So I've connected the motions with the coordinates. Okay, here's where the work begins. Let's look at mass 1. That's that mass that's on top. So look, mass 1, the force in the y or vertical direction is net force m1a1y is n1 minus m1g. So the normal force right here is just m1g, the weight, because it doesn't fly off the top. Okay, what about the x direction? What about the x direction for mass 1? Well, there's only one force, just the frictional force. So I can solve and say, well, the acceleration of mass 1 in the x direction looks like that. And see, it depends entirely on the frictional force, mu12 m1g. Okay, so that's the acceleration that mass 1 can experience. Let's talk about mass 2. Mass 2 is more complicated, right? So look, in the y direction, m2y, there's the normal force n2 up, that's from the table, n1 down, and then weight m2g. Now I know n1, I solved for it already, it's right, it was over in the previous problem, so I can substitute for n1 and get to n2. So this isn't surprising, right? The normal force n2, the force between the table and the block, is really the sum of the two weights. That shouldn't be surprising. Now the real work comes from this x part right here. The net force in the x direction consists of the tension to the right and then opposed by the two frictional forces. The frictional force from mass 1, the frictional force from mass 2. So I can substitute everything in and get this expression that still has a t in it. Okay, I'm going to get rid of the t because I have one more mass. So it's really a three equation, three unknown kind of problem. So the net force on mass 3, well, let's see, that's m3g downward. And remember, that's that downward is plus x, minus the tension upward. Okay, so I could solve for the tension. Now that I've solved for the tension, I could go back and plug it in to solve here. Okay, m2ax. So I plug it in, and I solve for the acceleration of mass 2 and mass 3. Okay, so if it turns out that this acceleration ax is larger than a1x, right, this acceleration here, that would mean that the m2 block accelerates out from underneath m1, m1 falls off. That's a hard problem.